there a clicker or
No, so we have to deal with this.
Clicker, but it's out of battery.
So let me try. Do I have to get go?
all right. Well, thanks to the organizer for inviting me. So I have to also thank Conrad, who did a very good job and basically explain what would have been a completely incomprehensible talk that's coming. So thank you so much. Just for placement, I'm a string theorist. I'm on the other side of the spectrum. So I'm happy to be here to learn about real physics, but you have to bear with me. So what I'm going to tell you about is, so I had one title which was kind of generic. This is also very generic, but my point is to make explain some important result, I believe, in the physics of black holes, and then I try to see how it might be related to applications to ADS condensed matter. So it's that's sort of the part of the talk. And most of this is work I've done with one of my grad students, Junxiao Zhang, and my longtime collaborator, Jun Yang from University of Science and University of the Chinese Academy of Science in China. Okay, so here's my my outline. So I'm first going to talk about this puzzle in black hole thermodynamics. I would explain what the puzzle is. So again, a lot of my hope is that I can convey some result. If you have questions, by all means, my goal is to try to be at least to be understood, whatever the formal part is. Then I will explain how this puzzle is resolved and it changes the thermodynamics of black holes at low temperature. And once, given what Conrad already explained very nicely, black holes are sort of like the first step if you want to connect to condensed matter. So then I will follow my nose and look at some of the typical computations one does in condensed matter from the ADSC point of view and see how it changes. All right, so that's the story. Good. Okay. So what is the puzzle? The puzzle was pointed out by this group here, Preskill Schwartz, not John Schwartz, but Patricia Schwartz, for people who care about these things. Alfred Shapir, Trivedi, and Vilcek in 91. So it's an old puzzle. I will explain. It's very easy to understand. So if you look at black holes, they have mass, entropy, charges. So this is standard from GR. But for a streamer black hole, a streamer means close to zero temperature. If you look at the entropy goes linear in temperature. This is what I sort of pointed here with a black line. But the mass goes quadratic with temperature. This is just a property of general relativity. You look at the solution, you try to take the small temperature limit, that's what you get. And what was pointed out in 1991 is that if that is the case, then there's some sort of scale that is called quantum temperature at which the entropy will dominate over the mass. And now if you emit a Hawking quanta that has energy proportional to temperature, so that means that just emitting one quanta completely destroys what you thought was a kind of equilibrium of the black hole. So that means that the whole thing makes no sense around this region. Right? So that's the puzzle, right? And it's very, very clear to see if you follow black hole thermodynamics.
So can I this
yes,
is
please,
a really
please.
dumb question from
Please.
So is that regime ever reachable in nature?
Right. So in nature, no, in nature, okay, there are two answers. So for the black holes that we care about that are electrically charged, etc., no, there are no electrically charged black holes in nature. But in nature, there are black holes that spin very fast. Those also have some sort of instability along those lines.
What I meant was the temperature scale at which this happens. Is that the temperature scale that can actually happen in nature?
No, it's too small. Too small. Yes. Yes.
I'm very naive.
Please. Yeah, naive.
So, in ordinary thermodynamics, so we can start with an equation of state, say for a classical ideal gas. And then we find that, if we try to take those equations of state and push them to very low temperature, then we get various inconsistencies. And that tells us that, there's a temperature scale below which we need to fix it.
Exactly. Yes.
That's
This is exactly the same thing. So black holes also at low temperature are quantum objects, and we need to be careful treating them because quantum fluctuations are very important. That's actually the main point. Yeah. All right. So
I have a pointer for you, but it doesn't.
It doesn't
treat
treat the
radius.
radius.
The USD is not good.
Okay, yeah,
That's why
sorry.
you don't.
all right, so good. So the resolution to this puzzle did not require that we build a full well-defined quantum gravity, right? So there's no need, yeah. So the answer to this question or a fix to this problem comes by understanding the specific modes. So some modes that become massless and they create this issue, right? So it doesn't require us to know a full theory of quantum gravity. It's a very controlled question that we can answer. And in fact, the physics underlying this resolution is precisely the physics of JT gravity. JT gravity was already mentioned as the ADS2 counterpart to SYK. So if we use that quantum physics, we might be able to understand this problem without having to understand, the black hole singularity or the Big Bang. So those we have no way to address, but this particular thing we can, because the physics there is the physics of some particular modes that we know how to treat. So that's the sorry. I guess it depends on where I click. All right, so I guess I mentioned this. Now, there is a difference between the black holes that we are interested because they come from higher dimension, ADS4, ADS5, etc., and the 2D physics of JT gravity, this jacket-type bond gravity. So a lot of times, or at the very beginning, what people did was to say, well, if I go close to the horizon of this black hole at very low temperature, they look like some sort of product. And because it's a product, I can think of this extra sphere as providing some sort of compact manifold on which I can compactify all the fields, and essentially I will have JT gravity times an ADS2. But I will argue that this is a dangerous thing to do. It might work in some cases, but it's I will explain why this is a problem. So, and in particular, if you come from the realm of black holes, so if a rotating black hole will not be factorizable like this. So for rotating black hole, if you want to understand their physics very close to this scale, you'll need to find some other way to do it. And these are some papers trying to do it. All right. So here is a warning from the kind of physics that I mostly do. So and why I was interested in understanding this problem more carefully, because there are some examples. So first of all, let me explain. There's a whole area close to string theory that tries to understand black hole entropy very precisely, right? So the area divided by 4 times Newton constant is what Hawking and Bekenstein and everybody is very stable. You can see from thermodynamics, but that's not the whole story. So that is unobservable. It gets quantum corrections at the quantum level. And one important part of the corrections are these log corrections. So these are, so if you find a way in a string theory to explain this thing, people are happy, but they are not convinced until and unless you do also this part, these corrections, because the correction really contain fields moving in loops. So that really tells you understood the physics of the problem. So that was done for the Stroman-Jebaffa black holes. But for ADS black hole, that was a problem. And so the problem is that there is a big difference if you're considering a specific black hole in ADS4 crosses 7. If you do the computation in ADS4, you will miss it. You will not get this coefficient. So you will not be describing the actual physics. So to do that, you need to be in the full 11-dimensional theory. I know this is a little bit esoteric, but this is a lesson that the field learned over a number of years, that the actual computation of the leading corrections to the entropy requires that you pay attention to the theory in the full space, not just in some dimensionally reduced case. I'm not going to go into details about this point, but the message is that you need to look at the higher dimensional story, not just the effective, very low energy discussion. All right, so now I will go into some details, but before I go into detail, I want to explain how we are able to see this JT physics in higher dimensional models of black hole, in particular in this rotating black hole. Rotating black holes are quite complicated. So if you understand something in that framework, you are more or less convinced that you did understand the problem. So these log corrections to the entropy were discussed by Strominger and friends, and also by this group of Rangamani, Turiachi, and friends. And the idea is quite appealing to me. So what you do is you try to compute your gravitational path integral directly in 4 dimensions. But what you realize is that there's some zero modes in this path integral, right? And if you have a zero mode, the determinant of the corresponding operator would be divergent. This would be infrared divergences that you need to fix. So the natural way to regulate these divergences is by turning on a small temperature. And after you do the computation with a small temperature, you will see that your entropy gets corrected like this. So it's a question of order of limits, what we learned from this slide, that the right way to understand this stream of black hole is not to go to 0 temperature and do computations there, but rather you need to be a finite temperature, do your computation, and then see what you are left with. So that's the message that was learned from considering this black hole, these rotating black holes. All right, so now I'm going, So now I'm going to say the same things using some formulas so that we see more or less where we are, because I want to show you, my goal is to show you that this is very generic, that all black holes that are near a stream of being rotating or charged will have this kind of contributions, completely generic. So I want to now move into a little bit some of the maybe more technical aspects. So any question at this point before I keep going? All right, so again, I want to emphasize that the gravitational path integral is not something that we understand to deal with black hole singularities of cosmology, but we know how to do it in the case where I have a few infrared modes that are misbehaving. That we know very well, and that's what I'm going to do. Very special application of this gravitational path integral. So I'm going to start by, I have some metric and some set of fields, I fluctuate them, right? And then my partition function will have part that comes from the on-shell action and part that comes from this one loop integral. In the case of the metric, this operator is called Lishnerovich operator. It's very well understood. And what we know is that, or what we see in this case is that if I take the temperature to 0, there are some eigenvalues of this operator that go to 0. Yes?
Yeah, okay, it's gonna be naive again, but I remember like taking quantum field theory.
Yes.
There was this trick where you could calculate the ratio of determinants using this, I forget, Yaglom, you
Just find Yaglom.
Yeah, that's right, that's right.
So you could do things like that as well. Of course. But here I'm interested in some specific modes, so I will show you the modes. I show you how I get their eigenvalues lifted, etc. But yeah, all this is precisely in the toolbox of computing path integrals. All right, so again, this is an infinite dimensional operator. Sometimes it's very hard to compute infinitely many eigenvalues. So this Gelfand-Yaglom trick is a trick.
You solve the equation of motion somehow.
Exactly, with some boundary conditions, and that gives you the answer for the product of all the eigenvalues. That turns out to be a meromorphic function, so it's very protected, etc. But here we don't need that much. So again, we are doing Gaussian, right? So it's not interactive, it's just Gaussian path integral. So you see that essentially this is the determinant, and there's a 0 mode, and that's my main physics. All right. So what I need to do, what I need to do is to regulate my background. So if I sit exactly on ADS2, I have 0 modes, path integral not well defined. So I need to turn on a little bit of temperature, deform my background. That will regulate the problem. I do that for all the fields. And then the eigenvalue that was 0 will now have some contribution, and it will fix my determinant that was infinite now will become a finite determinant. I need to use some regularization there too, because I have product of infinite numbers, but in the string theory, as you know, all this is minus 112. So we know how to deal with product of infinite numbers. So we get this 3 half. All right. So this is sort of the computation. This is the sketch of the computation in general. Now I want to move to a slightly more rigorous, just one last step of rigor. I want to show you that this computation is fairly universal. So I can do it not only for the curved black hole, but I can do it. My goal is to show you that I can do it essentially for any black hole in any asymptotic. So it can be in flat space, in anti-de Sitter space, or de Sitter space, and they always give me the same answer. So that's I think is quite nice. So I will in the next slide I will walk you through that computation. But everything that I have already said is the essence. So the rest now is a little bit housekeeping. I want to write a theorem, so I have to be careful with my conditions, etc. But that's where I'm going.
Should I understand this as a manifestation of the fact that you're insisting on looking at near extremal black holes that have an ADS2 somewhere in their geometry, and everything is being controlled by that, and it doesn't really matter so much how that ADS2 gets completed asymptotically?
Yes, that's exactly how to understand this. All right, so let's see the details. So the framework is this. I think also Conrad had an expression like this. So I can do it for in any dimension. I have Einstein gravity. I have a bunch of scalars that are not charged. So this is their action. And then I have a bunch of abelian fields, and I have a potential. So my idea that I can do this in any asymptotics is because I allow my potential to take any value, positive, negative, or 0. And then the actual second order differential operator on the metric that I need to take care of is this Lishnerovich operator. It gets contribution from Einstein, Hilbert, potential, etc. All right. Good. So I have some definition of black holes. This is a little technical. So about quadratic extremality. So it has to the temperature has to go to 0, but in a specific way. And on this gentleman here, Kunduri, Luchetti, and Real, a while ago, I think 2007, wrote a lemma that a black hole that is solution to the very general Lagrangian that I showed you before, all those black holes will have a near horizon geometry which is of this type. So here you should recognize the ADS2 part, but it can be warp. If you have many dimensions, there can be rotating angles, rotating plane, but this is the general form of the metric in a completely general theory of gravity. Now, what I need to prove is this, that for that very general metric, in the conditions that I explained, the Lishnerovich operator admits a 0 mode, and this is the explicit form, right? So it's some metric that depends on some number. This is a Fourier number, but this function is the one that you can compute from the near horizon geometry. All right, and then again, these are 0 modes for n greater or equal to 2. Maybe I did not write it, but 0 plus and minus 1 are the ones that correspond to ADS2 symmetries. So those are not lifted with this. And that's it. So with this, there's a little bit more technical. So let me now explain.
Sorry, Leo.
Yes.
Okay. I think I missed one slide where you showed the coordinate system that you were using.
I did not explain carefully the coordinate system. So let's see if I can go back. No. Oops. This is not good.
Time only moves forward.
Yeah, so I did not explain the coordinate system very carefully, but I can fairly universally define that coordinate system using some node coordinates close to the horizon. I can do it very
So
carefully.
here you're using this generalized ADS2 type metric that would also apply to rotating near extremal black holes.
Yeah. So it can rotate. So this is, this function will be theta dependence. If the black hole is rotating, it can rotate in any dimension. So that's why this is quite universal.
So theta are coordinates on the sphere.
Yes, that can be squashed if there's also axial symmetry. So the key thing is this is now I can prove this. I can prove this with a computation. This is a zero of the Lishner-Roche operator. But before I do that, let me explain the physics behind this. So the metric has some gauge symmetries, right? It's like you can think of this as a more general type of a vector. So these zero modes that I showed you in the previous slide, they are essentially generated by diffeomorphism. So there's some symmetries on the metric. These zero modes are basically diffeomorphisms of the metric. This is the metric at zero temperature. Now, what that means, normally, if you have something that is a gauge transformation, you throw away, right? That's how you do quantization. But in this case, you cannot do that because these are so the vector that generates this transformation doesn't die off at infinity. So essentially fixes some boundary condition or large gauge transformation. So that's the nature of what is going on. This is the vector that generates those diffeomorphisms. And what you can do is to connect those vectors that I showed you in the previous slide with the vectors that generate time reparametrization in the Schwarzian theory or in the JT theory, and you can establish a one-to-one correspondence. So the statement that I make about n being greater than 2 is because, again, you have to model out by the symmetries of ADS2. That's a small technical thing.
Rho goes to infinity.
Sorry?
Rho goes to infinity.
Yeah, so rho goes to infinity is the boundary. So these are fields that are not normalizable at the boundary, and that's why they define large gauge transformations. So the Lishner-Roche operator, they basically, I need to integrate these gravitons. What I need to evaluate, I evaluate explicitly this part, and what I end up with, this is the lemma, is that the only contributions to lifting this eigenvalue come from objects that are completely geometric. All the matter that was in there cancels, again, by explicit evaluation. So once you have that the Lishner-Roche operator can be lifted only by geometric objects, you're more or less done because you know that the geometry was very universal. That's the lemma that I showed you before. And with that, you are already in a good position to show that this is indeed true, that in any dimensions, and again, for any potential, as the temperature goes to 0, you will have this kind of contribution to your path integral. But so here I will skip this. That kind of contribution to the path integral implies, well, here it's written. I went into some detail about modes, but maybe that's not so important. So yes.
Are you taking the determinant before taking the, are you taking the t going to 0 limit after taking the determinant or before? I mean, is it?
No, I take the determinant and I see there's a temperature dependence there, and that's my answer. In my answer, but I will explain it. Well, here's this explanation. My answer also tells me that the black hole, that I cannot take t all the way to 0 in this approximation. I expect all the quantum corrections as I go further and further in temperature. This is only a computation of the gravitational path integral around and maybe slightly below this TQ that I introduced at the beginning.
I guess I've been so you are taking the tensor modes in the t going to 0 limit. So I guess, are you keeping the full thing or taking the t going to 0, the leading term, and then taking the determinant?
I take my background, I add a linear in temperature piece,
I see.
and then I do the computation there. That's
I see,
where
I
the-
see.
the
And
zero
then
modes are.
the extra pieces that you leave out, they are supposed to be subleading even after taking the data.
Yes. So I have to learn how to go back one slide back, but this is So I want to emphasize that so this theorem I organized with my student in February of this year, but before that there were many examples. So people were doing a lot of example by example. In all the examples, this 3½ number is correct. So the original curve computation is the one that motivated us. But then we did curve asymptotically ADS. There's Kerr-Newman in some complicated theories of gravity that are interesting for people who think about black hole. Also, there was some discussions about de Sitter. We extended our computation to Kerr de Sitter. And actually, more recently, there's this interesting paper that computed the same correction in higher curvature gravity. So the gravity that I explained has only two derivatives. I show you the Lagrangian, but there's explicit computation in higher curvature that is not included in my theorem, but that one is also give you this 3½ So this 3½ is super robust. It's something that is there if you want to study black holes at low temperature. And I have a summary slide here that essentially tells you the reason why this is so universal. So what really is crucial is the presence of this ADS2 throat, and this is true in any solution of the very general Lagrangian that I mentioned. I like to emphasize that there is a regularization dependent story. It's a little bit like there's some dirty laundry that I'm happy to discuss, but you are right if you don't like the zeta function regularization that I use, but that's an important point. But the key thing is that this received no contribution from the matter sectors. All the contribution to the Lishnerovich operator are geometric. And again, as I explained, this is true in asymptotically flat, potential equals 0, negative potential, or positive. And what we find by computing the partition function this way is that essentially we get sort of like the JT physics, right? So this is the formula of the partition function without this dangerous idea of that we reduce the theory to dimension. We do it directly in 4, 5, or 6 dimensions. And now it is important that if you look at now the density of states for a theory with this partition function, you see that the issue that we have in string theory for a long time about a large degeneracy of states at 0 temperature or very low temperature is attenuated by considering this quantum correction. So this is now some density of states that goes to 0 as you go to lower energies instead of having a very large degeneracy.
I guess you cannot trust it up till 0, right?
No, but it's good. So that, in fact, yeah. So I will talk about this is precisely, but the scale at which this becomes problematic is the scale of temperature divided by the entropy, which is a very, very small quantity. I will write a formula about that in a little bit. Yes.
I don't want to slow you down too much. I'm just trying to connect this things I think I do understand. So what you're saying is you can compute the quantum corrections to the thermodynamic functions of a black hole without actually knowing the quantum theory of gravity.
Yes.
Right, which is surprising given what we know about other quantum systems. So if I come back to like a quantum ideal gas, right, then if I treat that problem in a path integral formulation, actually, as you do, I can also try to compute quantum corrections. But then if I don't, then there are certain things that I will miss if I do something like Gaussian fluctuation. So for example, if I want to see the difference between fermions and bosons, right, then I need non-perturbative effects.
Yes.
Is there?
Yes. So that's absolutely correct. So this is what Trideep has been hinting. So here, if you wish, Yeah. So if you wish, in the JT language, I'm just using a disk partition function, but this partition function can have genera, right? Can have handles, etc. So this will also contribute to this expression at lower and lower temperatures. So I need to, yeah. So what I have done, as I said, what I have done is just address this little part around where they intersect that I wanted to see what's going on there. Below that, I have to crank up new physics.
I see.
All right, so these are the people who helped me. Here's my student Jin Shao and Sabyasashi and Niva. So these are the two papers of everything that I have more or less explained so far. All right, so Conrad also explained in much more eloquent ways what ADS-CFT has done for us, for the field. So clearly we have some question about the path integral, and we want to know, is this correction going to affect some of these interesting results in ADS condensed matter? Yeah, and what I want to tell you about now is about this computation that also Conrad showed in one slide. So this is very important for us because it's very robust, it's very solid. Again, whether this has implications or not for real physics might not be my main concern, but I'm interested in understanding how this computation changes under these new corrections. So that's what I want to tell you in the next few minutes. All right, so this formula also appeared before in Conrad's talk. So that's the ADS-CFT formula. And but now what happens in most of the applications that we use is that we are happy considering only this term, right? But now we know that this at zero temperature, this is not even a well-defined question. We need to include these corrections. So that's what I want to do now. I want to repeat this three-line computation of 1/4 pi, but now taking this piece into consideration. All right. Good. So because I already explained some of the details of the computation, I can now be a little bit more general. So this is the key. This is the key new ingredient. Now there are going to be two pieces for this eigenvalue that it was 0 originally. So there's the part proportional to the temperature that we used to turn it on as a regulator. And now there's a correction to the eigenvalue that comes from the fact that we need to have the graviton, if you wish, turn on, right? The perturbation to the stress energy tensor, we need to turn it on to test viscosity. So this is essentially what I have said. There are two corrections. This correction is the one that comes from the operator or the bulk field that couples to the operator that I'm interested in the ADS-CFT dictionary. All right. Okay, so this is something that people tried a long time ago. In particular, there's this paper of Edalati, Hotard, and Lee, where they tried to compute transport at zero temperature. But of course, back then the easiest thing to do, and then the most natural thing to do, was to set temperature to 0 and do your computation. But I already warned you that will not be correct. So you have to do your computation at some finite temperature and then see what the limit to temperature goes to 0 tells you. So there's one field that essentially becomes some scalar. This is the perturbation, the shear perturbation, but essentially this is the equation. Maybe I will not go into a lot of details about overlapping. This might be useful if I go into some details later, but for now, let's assume that this is part of the dictionary. So first I want to do, what I want to do first, there are two things, two sort of effects that are competing. One effect is, I said I need to turn on some temperature, but I also need to include the one loop corrections of this mode. So what I want to show you in this slide is some sort of sanity check where I turn on a little bit of temperature and I look at this is the retarded Green's function. it gets a term that is proportional to the temperature. And when I apply the Kubo formula, I get that the viscosity is given by this formula, and the entropy, the three-level entropy also gets a contribution, but they precisely contribute to give you 1/4 pi. So if you do the computation at 0 temperature, which is what Rob Levy and friends did, you get 1/4 pi. If you turn on a little bit of temperature, you still get 1/4 pi. And in fact, so Jim Lewis is my colleague in Michigan, and Alex Bushell was postdoc, also in Michigan. But they show that in any theory, in any gravity theory, it's two derivative. If you do this computation, you will always get 1/4 pi. So what we have done is nothing but a sanity check, right? So we turn on a little bit of temperature just to make sure about the order of limit, and we get that if you stay at tree level, if you do not include one loop corrections, you obviously get 1/4 pi. So that's a sanity check. What is interesting is that I can turn on the source, imposing boundary conditions. This is just a little bit technicalities. When I do the computation, I want to show you a little bit of the details because I already tortured you with this computation, so I can do one more step. So this is the lifted eigenvalue that we computed before, right? But now I want to compute it in the presence of this extra mode, this shear mode. And what I obtain is that there is a contribution to the lifting of this eigenvalue only for n equal 2. I tried to convince you that there's a one-to-one correspondence between the Schwarzian modes, epsilon n, if you like your SYK, and this tensor mode. So all other modes do not get contributions or do not couple to the shear perturbation. When you evaluate the one loop determinant, you have the infinite product we have before, but the n equal 2 is the one that is affected. This part contains the source, if you wish, this C1. So when I compute, so this is a little bit of the detail of the computation, but I think it might be useful later. So the one loop, when I compute the retarding green function using ADS-CFT dictionary, I get that there's the three-level piece, but there's a one loop piece that comes with 1/temperature. So I put together the correction to the green function and to the entropy, and I get a formula like this. So this is what I show you without this part, right? So this is the quantum part. This is the part that will have been 1/4 pi. So I just rewrote this a little bit to show you that you have almost 1/4 pi, but you get this 1/t correction in the numerator and log t corrections in the denominator. So that changes. It's better if I show you a plot. So this is the plot of what you see. The 1/4 pi that was completely universal is now not precisely the answer. The answer has this feature. I would say in a few words what this means, but essentially it's a competition between 1/t and log t. So that's what is going on. So before, again, in all previous computation, completely universally, this was a featureless temperature independent answer, 1/4 pi. Now it does depend on the temperature in this non-trivial way. Yes.
Actually, in the first part of your talk, it was only around TQ essentially where this was developed.
Yes.
How does that work here?
Yeah, so I'll explain right here. So here also it has to do a little bit with TQ. So first, let me explain that at very, very low temperatures that are suppressed with respect to the entropy of the black hole, I expect completely new physics. In particular, the entropy there can become negative. So clearly that's a region, but this is very far away from the feature. The feature is happening around this scale. So I have TQ, but I had also chemical potential. So the scale at which this is happening is way above TQ. So that's what is. And again, what I explained before is that the curve dips below 1/4 pi because we have, for large t, the 1/t decays faster than log t. There was many confusing statements before. And so my main message, of course, if that has not yet been clear, is that T to 0 first is not the right way to tackle this problem. But people have some interesting intuition about, you get some freedom about how you treat T if you have a large chemical potential. But now that I have done the computation, I can see how this depends on the chemical potential. So here I have temperature, and in this axis I have chemical potential. So it is true that if you go to large chemical potential, this seems to be 1/4 pi. But if you follow in the order of limit, you can see that if you are always at temperature, non-zero temperature, you'll have an influence of the temperature there. So that's so I have to say, well, okay. So similar computation, similar quantitative result. I have yes.
You had this interesting geometric mean of square root of
Yes,
mu and TQ. Does TQ depend on mu actually? I mean, are they really two separate scales in these problems?
I think they are separate, but I mean, it all comes back to the black hole formula. So I'm not completely sure. Yeah.
Okay. But I mean, it's a very interesting result, right? You can see these corrections even.
So what I explain is this sort of higher dimensional point of view. So there are similar qualitatively similar results obtained using directly the Schwarzian theory. So you do reduce, go to 2 dimension, and these are these papers. So Bless here, and then Kiritsis, Samir, and also Sarah Cremonini. So they discuss this computation, but directly from the 2D point of view. Now there are some differences. Maybe it's a little bit too technical to discuss, but let me point out. So my computation, my higher dimensional computation is just a one loop computation free. So you can argue why you're missing interactions, you're missing many things. So I have a limited regime of validity of what I'm doing. I'm not claiming. So I would like to say that again, it's something that helps me understand the physics around TQ, maybe a little above TQ, but certainly not very low temperature physics. The 2D point of view has a better chance of being a good approximation for smaller temperatures. And but what they find is that all these papers is that for T a lot less than TQ, again not close to the regime where it breaks down. They find square root. So what I explained to you, what I find is essentially this T over TQ or 1 over T. So that one is a little bit of that's something we need to clarify. But what I expect is that in my model only one Schwarzian mode coupled to the shear perturbation, and in this 2D because your green function is such that all Schwarzian modes couple. So that's one place where one might see such a difference, but there's some sort of like overlapping regime if you express the shear viscosity in terms of energy. You'll see that you can sort of interpolate between these two regimes because the energy, depending on temperature, this is the semi-classical dependence. So you will get something like this. But in the quantum regime, once you have corrected, you will get something like that. So yeah. So that's sort of what I wanted to say about that.
Leo?
Yes.
So you're right that both approaches get a 1 over T correction.
Yes.
But it looks like the coefficient is not the same in your approach and also in that other approach. And do you have any insight where the discrepancy is coming from? Because ideally,
yes,
we'd like to all compute the same number, not just the same temperature.
Yeah, I don't know exactly. My only clue is that there's in the high dimensional approach, it looks like only n equal 2 modes coupled to the shear, and all these other modes they contribute to the path integral, but they do not couple to the shear. Whereas I think in this 2D approach, everything all the modes are coupled. That's the only thing I have at the moment. But yeah. Let's see where 10 more minutes. 10 more minutes. Okay. So. Okay, so things I'm thinking about in the future is, of course, try to understand why in the deep quantum regime we have completely not even qualitative agreement, but not even qualitative agreement. And there are other questions that I'm interested in looking at, like this electric conductivity. So since I have like 10 minutes, maybe I tell you a little bit about electric conductivity and bigger puzzles. So this is about black holes. I don't think this audience is super interested. But by the way, if you remember Conrad's explanation that the viscosity is related to the area of the black hole and that was related to absorption, people have computed the quantum absorption of these black holes, and they agree. So that's one of the things that one of the sanity checks with the answer, that the answer that we have for viscosity agrees with with the computation of shear of black hole absorption with these quantum corrections. That's actually not true. All right, so now I want to tell you a little bit about conductivity in this framework. So again, now we have some four-dimensional Einstein-Maxwell with a negative cosmological constant. Again, I need to fluctuate. There's some dictionary that tells you what to do. I need to fluctuate the bulk electromagnetic electric field. That's the equation. This equation is useful because, okay. So from there, and again, I'm quoting what people did before by sending first the temperature to 0 and then doing the computation. So actually, this is what Rob Lee obtains. So he obtains, because this is the regime in which temperature goes to 0. So he obtains 0 DC conductivity. You can be a little bit more careful and have this limit. This is the classical, right? What I mean classical is without any quantum corrections, all right? So you get some temperature squared. But this is what we want to now see how it gets modified once you include the some quantum corrections. I am now going to jump. I will tell you the computation from this two-dimensional point of view. The authors that I quoted at the beginning, at the end of my first part. So here you have, this is your whole space-time. At the boundary you have, the boundary of say DS4 is where your field theory lives. Then you have a very low temperature. This region is very large. This is a large throat. Here is the place where the Schwarzian quantum fluctuations are localized. So here's the horizon. There's an overlapping region where you want to make things, if you want to solve this equation with some boundary conditions, you want to make sure that you have this overlapping region. Now I'm going to switch gear, as I said. I'm going to now do this computation not by looking at the gravitational path integral as I have done before, but by taking this sort of picture. So what I'm going to do is to connect some retarded Green function here to a retarded Green function in this region, and then assume that this one gets quantum corrected by interacting with the Schwarzian. Okay, that's a slightly different framework, but that's what I'm going to do. So, yes.
2 slides ago, I just want to make sure that it wasn't a typo and it was really correct. You had that the conductivity is scaled as T squared. So, which is, usually we think about the resistivity as being an increasing function of increasing temperature. So this is, totally flipped around. That was correct?
This is the correct answer for this classical thing. Yeah.
Okay.
Here, what Leo has in mind, this is still a translationally invariant system.
Yeah.
So only the DC conductivity is infinite.
Yes.
But its real part, the real part of the frequency-dependent conductivity, has a finite contribution at 0 frequency. So there's an I over omega pole in the imaginary part due to translation invariance.
Right.
But then there's a finite real part, which is the same sigma q that Conrad was talking about.
Okay.
And it is that piece that goes like T squared.
I see.
So this is not really comparable to the resistivity that you have in mind, because the resistivity that you have in mind is actually the full omega to 0 limit of the system when you relax momentum. Thank you.
Thank you so much. Also because yeah, it's good to have this interpreter. All right. So again, I'm now just follow some sort of algorithm. So I told you, I show you my picture. So I need to know what kind of field I'm going to couple to the Schwarzian theory that lives in the throat. And I look at the equation in the ADS2 throat, and this tells me, okay, you're talking about an operator of conformal dimension 2. And so this started its life as a perturbation of the bulk vector potential, but in the region that I'm interested, it becomes some sort of neutral massive scalar with which couples or is dual to an operator of conformal dimension 2. With those ingredients, I can compute the DC conductivity, modulo translational symmetry, etc. And this is what happens in the very small temperature regime. This is the quantum regime. So there's also this feature that it has a minimum, then it increases. This is still work in progress, so I'll show you why there's some issues. But again, in this framework, with this approach of taking turning the computation into some effective computation in the Schwarzian theory, this is what you get for the DC conductivity. Yes. What is C? I missed that. C. Okay. C is 1 over TQ. Yeah. Sometimes in the literature people call it C. I like TQ, but unfortunately, yeah, I made some mistakes. But yeah, it's the scale at which these corrections are becoming important. Yes.
I mean, it's non-monotonic, which is interesting. Yes. Is there any qualitative way of understanding what's happening as you cross through TQ that's making it non-monotonic?
I don't have a deep understanding, but this is so this I have checked very carefully. I have tortured my students with do it numerically, do it this way, do it that way. This is robust. So oops, okay, good. So this is optical conductivity as a function of omega. It has these features. Again, the computation is pretty robust. Let me end. I think I want to end with a puzzle, even a more complicated puzzle than what Blaise alluded at the beginning. So if I were to do the computation in 4D, this is the answer for the imaginary part of the retarded green function, which is quite different from anything I get here. So that's very confusing to me. If before I had this idea that, well, in the shear viscosity, only the n equal 2 mode was coupling, here essentially all Schwarzian modes are coupling, so that cannot be the answer. But that cannot be the answer to this sort of discrepancy. Yeah, so this I think that this is my last slide. I want to end up by thanking everybody and just leaving this as a puzzle. I try to understand it.
Questions.
Yeah, so when I looked at the vertical scales, the corrections to the shear viscosity to entropy ratio were like the 4th decimal point. So it was very small, but the corrections here to this incoherent connectivity was appreciable. So do you have any understanding why it affects the connectivity more in the relative sense than the shear viscosity ratio?
No, nothing super deep, except that I know that eta over S is very robust, so it's hard to make any change unless there's some deeper physics. Here, I think, I don't have much deeper understanding, except that I think the story with the Schwarzian theory allows you to have bigger corrections to whatever your standard idea is.
This is a totally stupid question, but so you've been computing, quantum corrections to various quantities.
Yes.
I guess there are quantum theories of gravity, like string theory, some versions of it, where you can actually do full quantum mechanical calculations. What do if I take one of those theories as a model theory of quantum gravity and take it to low temperature, are there yet more interesting exotic corrections that come in? Anything that's kind of, qualitatively beyond what shown us here.
Yeah, so yeah, unfortunately, string theory gives you some understanding of quantum correction, but it's not in a very explicit operational way. So we know, space-time can be emergent. So most of the progress that has been made recently is by identifying specific questions that can be answered without having to use this full machinery of string theory. And other theories of quantum gravity, like loop quantum gravity, etc., I don't think they are at a level or either that can help you do computations there.
Thank you.
Anybody else? Well, thank you so much, Leo.